everyone coming. So it's my great pleasure to introduce Professor Daniel Spector from the National Chiao University in Taiwan, and he is speaking about the Taylor approximation and then Sobolev spaces.
Thank you for the opportunity to speak and the invitation. It's always a pleasure to visit SIU. It's hard to believe that I've been visiting here for over 30 years. Some of you won't believe it. You know, when I first came, it was just to socialize with some of the members of the department, and then give a couple private lectures. And now I think maybe the audience is a little bigger and more interested to hear a little more about what I have to say. So, what am I going to talk about today? It's going to be about some research that's just appeared. So this year is 2016. It's just appeared in June of 2016, and it's on Taylor approximations and Sobolev spaces. But actually, it appears in 2016. It's maybe 3 years old. 2013, I had done most of the work on it. And I've come back here and I've spoken about Sobolev spaces many times. And I'm actually very thankful for these opportunities to think more about how to take what you study at the graduate level and then how to, not distill it, but maybe like present it in a simpler way. And keep working and keep working to present it in a simpler way until actually Colloquium organizer last year asked a question. And this question was kind of the basis for how I was going to present it in this talk. So, what are the Sobolev spaces? They're an example of an infinite dimensional space, and so we should maybe start in finite dimensions if we're going to get an understanding by analogy. So, if we're going to start in finite dimensions, why don't we just start with one dimension, and let's talk about the real numbers. So now let me open up to the audience, and we'll get some input here. I have some notes, but when you think of the real numbers, how do you think about defining them? How do you think about the real numbers?
You take a calculator?
Perhaps through a tree.
Through a what?
Through a tree.
Through a tree. Can you say more about that?
Yeah, so take an infinite binary branching tree, take paths through that tree, modulo some appropriate and not too difficult equivalence relation.
So you're talking about a decimal approximation, is that right?
I'm talking about a binary. Well, no, not binary approximations.
Depends how many branches the tree has.
But in any case, it's binary.
It's binary, not decimal approximation. So you're talking about an approximation. So if it's binary, you're talking about...
No, those would be the finite paths.
The finite paths.
The infinite paths are not approximations.
Are not approximations.
They're
But
the full thing.
a real number is anything that you can go all the way through. And you can write down a...
Yes.
That's
okay.
not to think about what they are. Take a more Buddhist approach to it.
Okay.
Which is where it came from. The continuum came from the Indian tradition.
And so the definition that you would use for...
Well, I make my students do deacon cuts, but we don't want to do that.
Yeah, so there's that approach too. And so I had written down actually two other ones that I thought about. And of course, if we're talking about the same real numbers, then they have to all be equivalent. But the two that I thought about is people can picture what a rational number is. A rational number is any p over q, where p and q are integers and q is not 0. So the rational number is a set of all these, and then if we define the integers, then we have to, if we use the integers, we have to define the integers, which are the natural numbers, their inverses, and 0. And so then we should start maybe with the natural numbers. And so somehow we arrive at q. Whether you go this way, or you use some axioms, some field axioms, you arrive at q. And what differentiates q from r is something else. And the way that a lot of times I think about it, we teach calculus, we say you look at sequences of numbers, so like a square root of 2, you think about 1.414, maybe you know some more decimals after that, I've lost them right now. But you think about, if you look at the finite, the truncations, and then you keep adding, then you end up, all those sequences, you end up with real numbers. And what this approach is this approach is thinking about, you have this set, and there's a function, which is the distance, from x to 0, so the distance from x to 0, and this set with this norm is not complete. So if you take q and you complete it in this norm, what you arrive at is one definition of the real numbers. But I looked through some books, and most people don't define it that way. Now this is the intuitive definition for me. Let me ask you, do you agree? Is this an intuitive way to think about it, or am I just thinking about this?
It is an intuitive way, yes.
It's an intuitive way. But it's not the way we do it in the books. What do we do in the books?
Depends on the book.
Depends on the book. I picked up one, and we have the lub, right? The least upper bound. And it's an axiom because it's what makes it into the real numbers. So every set which is bounded above has a least upper bound. And you contrast these two kind of definitions. You know, you build the rational numbers, and then you either complete them using this kind of like any of the Cauchy sequences, or you add the least upper bound property. And you have two different kind of approaches. And I think the reason that we do this way, so this is maybe for me the intuitive way, and this is what I would call the comfortable way, is because you're more comfortable proving things with this definition. You can prove a lot of things very quickly with this definition, that maybe it's harder to verify in this. And maybe the difference is small with this, but when we get into what I'm going to talk about, this is an important distinction. The intuitive way versus the comfortable way. So, before we get to the Sobolev spaces, let's kind of do some warm-up to get there. And the warm-up we want to start talking about is we want to start talking about the space of Lebesgue interval functions, so the space L1 functions. And if we're going to get there, then let's start with something a little bit easier, which is to start talking about continuous functions. So a continuous function is a function for which, if you look at f of x plus h minus f of x, that this difference goes to 0. That's continuity at the point x. And if we assume that f is identically 0 outside some interval, so you take, we'll just work on the line right now. This all works in more dimensions. We'll just start a line. You take a function which is 0 outside of some interval, as this has compact support. For these functions, it's very easy to define integration, because we don't even need Lebesgue integration. We can define integration of these functions by just writing down this integral. And when you have a continuous function and it's 0 outside of some set, then what you mean is the Riemann integral. And even better than the approach where you chop things up and you allow it to be any point in between, something I actually like, there's some notes on this in several dimensions, that if you take, say we just take the interval 0, 1, and you chop it in half. And then that's your first partition. And then on the next partition, you just chop these two in half. And on the next partition, you just chop each of these in half. So you're working with dyadic partition of the intervals. And then if it's more than 0, 1, you just, it happens on a bigger interval. If you define it this way, and you look at in any given interval size, so when there's k divisions, we'll call the big set ik, the set of all these things, which has little I, so this is I1, I2, I3. So you have, for any ik, if what you do is you sum over the ik, so you sum over the little ii, and you look at the sup over x in ii of f of x, then this gives you, you're choosing a point in the interval. You're choosing the sup, and since f is a continuous function, it's actually the max in the interval. Then you multiply by the measure of the interval, and this gives you a upper sum. So this is what you call a uk of f, is an upper sum, and you can define a lower sum of the imps and you say that a function is Riemann integrable if the limit as k goes to infinity of the uk of f is equal to the limit as k goes to infinity of the LK of f. And then more functions are actually Riemann integral than just continuous functions. If you take bounded functions and you use this as a definition, whenever this holds and they're Riemann integrable, then that's fine. But in particular, you have it for continuous functions, and so if you take a continuous function, you can very easily use this to compute what the integral is equal to. You chop it up and you take the pieces. And this is integration for continuous functions, Riemann integration. And then that's undergraduate analysis, and then we go into the graduate course and we define the Lebesgue integral. And we don't do it this way, do we? We don't start with Riemann integration. We have another approach. And this is what I'm talking about here, about the intuitive approach versus the comfortable approach. Because the intuitive approach, right here with this, would be to say, let's take the set of all continuous functions with compact support. This is a set of functions. All these functions have finite Riemann integral. And let's complete it in this norm here that I've called conveniently L1. Let's complete it in this norm. And when you do this, you get the space of functions which are Lebesgue integrable with finite L1, with finite integral. So you look at all the Cauchy sequence and you get this. But why don't we do it this way? Unless I found one book, Peter Lax's functional analysis book does this at the back, but I haven't seen this done very many other places. Because then every time you want to prove a property of the Lebesgue integral, you have to go and you have to take an approximating sequence and you have to check to see if, when you do things in the approximating sequence, if you're able to prove the things for the limit. And if instead you start with the Lebesgue measure, and you construct that, and you use the measure to construct the Lebesgue integral, and you use the Lebesgue integral to construct the space L1. Then when you construct this, there are certain properties that come with it. And then these properties are inherited by the integral and they're inherited by the space L1. And so this is typically how it's done. Now, what's going to be important is something that comes up in this example that isn't really exactly, I couldn't think of the analogy in finite dimensions. But it comes up here. This is a continuous function. So you might ask the question, this happens for continuous functions, that if you look at f of x plus h minus f of x, this goes to 0. When you define the space this way, as a completion, maybe you expect certain properties to be inherited for the space L1. For example, is it true that this holds for an arbitrary element of the completion?
Absolutely not.
Absolutely not. That's right. So if it held, then it'd be a continuous function. But there are functions here which are not continuous. For example, if we take 1 over the square root of x, and we're just talking about something which is locally, so you take something which is like this, and this has finite integral, but this function is discontinuous. And you say, yeah, well, that's just discontinuous at one point. That's not so big of a problem. You take this function, and you look at it, and you translate it, say Rn, where Rn is an enumeration of the rational numbers in, say, -1, 1. And then you take 1 over 2 to the n, and you sum this up. So you take these things, and you're moving them around, and you're shrinking them down, and you have something which is very bad from the continuity standpoint. But each one of these terms, you can verify, this has a finite integral. And so when you sum it up, you get some number, and the 1 over 2 to the n is summable. So this defines a function which is actually an L1. So you might wonder, well, this doesn't hold. Is there some property which is inherited by the functions in this space L1? And actually, it's a very nice, very easy thing to write down, is that if you look at this, and you don't get this, but if you take it and you integrate it from minus epsilon to epsilon, so you go in a little interval, and it's an average, so this is that, and then you're averaging it, so this is order 1. And then you look at the limit as epsilon goes to 0. it is true that this is equal to 0 for L1 functions for almost every x. And that almost every is in the sense of Lebesgue measure. So there is some property that is inherited. So you have the continuous functions, you have the space L1, and so if you're continuous with compact support, that means you're in L1. If you're in L1, that means that you have this property. This is called the Lebesgue differentiation theorem. So you have Lebesgue differentiation.
Effectively, you're saying that L1 functions are continuous on average.
On average, that's right. That's exactly what that's saying. But the converse is not true. L1 is not continuous. You pointed that out very well. Lebesgue differentiable is not L1. And you have to think maybe a little bit more to come up with something there. I just wrote down an example, and forgive me for getting over here in the corner. And then I promise I'll erase everything, and then we can start fresh over there. But if you take a function, which is like a box with width 1 and size 1, and then you put on top of that a box which is width 1/2 and size 1/2, and then you put on top of that a box which is width 1/3 and size, with size 2, width 1/3 and size 3. So every time you're having something which has area in there 1, and you can write this down as the sum from n equals 1 to infinity, the characteristic function of the interval 0, 1 over n, times n. Right? Because when n is 1, we get this piece of it, and when n is 2, we get this piece, and then you're adding it up, so that's why you put it on top. And you build in this way a function which for each x is actually finite. Because if you take some x which is bigger than 0, x is here, and you only have one term in the series. Or x is, maybe it's close to 0, but you only have a finite number of terms in the series for each x. This is well defined. When x equals 0, well, these are this open interval, so it's 0 at 0. So this function is actually defined everywhere. And for this function, if you compute, let's compute this right here. So you go to one of the points, you go to one of the x's, and you're right here, and you look at f of x plus h when epsilon is small. And when epsilon is small, all you see is this little flat piece right here. Right? When epsilon gets small enough, you only see the flat piece here. Or if you go and you pick your x here, when epsilon is really small, you only see the flat piece. Now there's no uniformity in the epsilon here, but for any x that you pick, when epsilon is small, this and this are equal. So for small epsilon equals 0. So this is a function that satisfies this at every x except for at 0. If you're sitting at 0, then you get a problem, because you try to integrate to the right of it, you get a problem. So when x is not 0, so it satisfies this for almost every x. But if you try to integrate this, you sum up 1 plus 1 plus 1 plus 1, you sum up and you get infinity. So this is a function which is not in L1, but it does satisfy this Lebesgue differentiation property. And this is what's in the background for when we get to the Sobolev spaces. So let's move up again, work to the harder lifting, and see what happens here. What week in the semester are you here right now? The third week?
Somewhere around there.
So what
Maybe
has
second, maybe fifth.
within an epsilon? So around the third week in the semester, I guess we get the definition of derivative. Have you started that yet? What's that?
Calculus, yes.
In calculus, yes. So the definition of derivative. Function is differentiable if the limit as h goes to 0 of f of x plus h minus f of x divided by h exists. And in that case, we write is equal to f prime of x. Actually, for me, a more convenient way to think about this is to write it as f of x plus h minus f of x minus f prime of x. And then if we move it over, then we have an h here and an h here. A function is differentiable if there is some function f prime for which this limit is equal to 0. So here you have the linear term in the Taylor series, and so a function is differentiable when it has a first order Taylor approximation. And f is C1 if this function f prime is continuous. I always have trouble with that one. I'm still not sure if it's right.
It's an approximation.
It's an approximation. Okay, so we started with L1, and we say L1 is just the continuous functions completed in the L1 norm. So Sobolev spaces, what are Sobolev spaces? We write down W1P, or let's just talk about W11 today. These are functions which have one derivative, which is in L1, which is integrable. And if we're going to talk about having one derivative, we should start with this definition of derivative, and maybe we can work from there. So the functions that are C1 and have compact support, so these are functions that satisfy this property for every x, and the derivative is continuous, and then they're all 0 outside of, I would say, a big ball, but we're in one dimension now, so they're 0 outside of a big interval. And if you take these functions, then you can make sense of the integral of f, because it's continuous and it has compact support. And you can make sense of the integral of this object f prime, because this is a continuous function. This is a continuous function which is 0 outside of some big interval. And so we can just integrate it using Riemann integration. And this defines what I would call the norm on W11. But this is not a complete space. So like the rational numbers, like the continuous functions in this norm over here, this is not a complete space. And so one definition of W11 is to take this space and to complete it in this norm. And this is what I call the intuitive definition of the Sobolev spaces. You just take the function to satisfy the classical idea of differentiability, and you just look at the completion, even if it's hard to think about what exactly it is. And this actually was probably the first definition. You never know who was the first person to think about these things, because maybe people don't write these things down. But actually, this is a definition, or very similar to a definition given by Beppo-Levy after the introduction of Lebesgue integral. And so you may be wondering why we don't call them Beppo-Levy spaces. And actually, it's interesting. So they asked him, so I think it was the French mathematicians in maybe the 40s or 50s, that asked Beppo-Levy, can we name these spaces after you? And I guess he was a humble guy, and he politely declined. And then later they asked Sobolev, can we name these spaces after you? And he said, okay. And so we call them Sobolev spaces now. So we have the intuitive definition, and then we have Sobolev's definition, which isn't too far off. It's not too bad, because if you start with the differentiable function, eventually in Calc 1 we go through and we say, well, if f and another function v are both C1, then we can write down that the integral of f prime v, and this integral is over R, except for these functions have compact support. So there's 0 on the boundary. And if there's 0 on the boundary, then when we do integration by parts, and we lose the boundary term, and then we get f prime v is f v prime with a minus sign, and we can integrate by parts whenever f is C1. But actually, if v is C1 with compact support, we don't need to ask that f is a C1 function. We could say, suppose f is a nice integrable function, and suppose that it satisfies this property where this object is not this one right here. Right? This is something else. You could write f prime, but you should really write something else. Suppose there is a function that whenever you have f v prime, you can just rewrite it as this other function times v, where this is also an integrable function. And now I see we're getting into the place where it's like this is the more comfortable definition, because you can prove many things if you can use this property. It's a very useful property. You can prove many things about these functions when you start here, but then it gets a little bit more abstract. It's much nicer just to think about, I know what these functions are. I know what the Riemann integral is, and I can pass through that. But you can do a lot with this definition, and Sobolev proved many things with this definition, embedding theorems and many things. And so you have these two ways to approach the Sobolev spaces. But what I'm telling you about today in the research is kind of a third description of it, which actually is going to parallel what we talked about here. So we have this. Let me erase what I've done over here. Let me write it again.
But it was 1964 before they realized that those were the same.
It's true, it wasn't right away. So, the limit as h goes to 0, f of x plus h minus f of x is equal to 0. The limit as epsilon goes to 0, 1 over 2 epsilon. So this is a continuous function, this is an L1 function. Well, before we get to this, let's just talk about the difference. We have a difference between the continuous functions and the L1 functions, right? L1 functions don't necessarily satisfy this. We have the same thing going for the completion, that there are functions in this completion that don't satisfy classical differentiability. For example, if we take a function which just looks like this, so we take 1 minus the absolute value of x, and then we just want to make sure it's 0 here, so we'll take the positive part of that. 1 minus the absolute value of x is a function. We have a kink, so we have it here, here, and here. And so this is a function which is not differentiable at this point, and at this point, at this point. And then just like before, we can take this function, and we can move it around and rescale it. So we can take 1 minus x minus Rn, positive part, 1 over 2 to the n, and sum from n equals 1 to infinity. You take a bunch of these, and you push them down, and you move them around, and you end up with a function which is in W11, so it's in the completion. But that isn't satisfied at any of these rational numbers. And I'm not sure, but I don't know where else it's satisfied. So the set where it's not differentiable, it may even be bigger than those set of rational numbers. I think a question I want to think about in a little bit. And so we have continuous functions, our L1, our Lebesgue differentiation theorem. And so here we see that C1 with compact support are W11. And so you may wonder, you have 1, 2, 3. Is there possibly some kind of theorem like this that's inherited by the W11 functions? So these functions are not C1, but maybe they have some kind of property which looks like this. And if you look over here and you look at the difference between these two, you might be able to take a guess that if you just add the integral. So if you take the integral of the difference quotients, it is true that the limit as epsilon goes to 0 of these difference quotients. You just add one integral, and you get this property. And I don't know whether, sometimes you wonder why people prove things when they did, whether they weren't thinking about it or whether it wasn't important to them, these kind of things. But Sobolev's papers are from the 30s, and this is from 1959, 1960 for Sobolev, and also for functions of bounded variation. This is a result of Calderon and Zygmunt. And so this is called, right here it's called L1 differentiability. So we have C1C implies W11 implies L1 differentiability. We know that there's no going back. here. We've seen an example that this is not true. And what's an example that L1 differentiability does not imply W11? What's an example of this? Actually, the same function that I wrote before, so you could choose a lot of functions, the same function that if you sum the characteristic function of 0, 1 over n times n, this is an example of L1 differentiability. It doesn't imply W11, but it doesn't imply L1. And why is that? This function, which I think it helps when I draw the boxes, right? Actually, I should have drawn it like this, because this is 2, and then a third, and then it goes up 3. This is a function that, away from these problem points, which is a countable set, right? You go here at 1 and a half, at a third. Away from that set, this is a function that f prime is equal to 0. So you take this function, and you plug it in here, and you're looking at, this is 0. You're looking at f of x plus h minus f of x. You look at some f of x and you fix it. Whenever epsilon is small, you're in some place where you're just on the flat spot. So this is 0. This is equal to this is 0, so it doesn't matter, you're dividing by h. So this is a function which is L1 differentiable, because actually this is true. Whenever epsilon is small, this is equal to 0. But it's not even in L1. So of course, if it's not in L1, then it can't be in W11, because the W11 norm has this, and it also has this here. And that was actually the state of affairs of the research. I don't think people were thinking about the fact that this doesn't imply that this is L1. I don't think that was necessarily important. People were interested in the properties of L1 functions that implies this, but the fact that this is not true wasn't really something I've seen written in the papers. But it is clear that people were thinking about the fact that this doesn't imply W11. People thought about that. They said, well, maybe we can assume a little bit more, and we can get a result which implies W11. So this is a result of Bagby and Ziemer. From the 70s, in which they assumed maybe something a little stronger than L1 differentiability, and they were able to prove it implies W11. So they gave a partial converse. And I say partial converse because if you assume the function is in W11, then this happens, just like before. Actually, it happens for almost every x. And what they assumed is they assumed something that happens for every x. So you assume something happens for every x, and then you can get backwards. And if you start here and try to go through the loop, and you say, assume it happens for every x, and then you're in this space, and then it happens for almost every x, but you can't get rid of that almost every, because an arbitrary element of this space is never going to have it happen for every x. For example, this function, it doesn't satisfy it here. Right? It doesn't satisfy it. It's almost every x, and this is actually a spot that it fails at. You try to compute the difference quotients, and it blows up. So they gave a partial converse, and so I don't know how many people were thinking about this, but people were thinking, they were thinking about it, can somebody give a full characterization in the spirit of this condition right here? And that was something that I hadn't known about, I hadn't thought about. It was only related to my research because I found a characterization of Sobolev spaces when I was working on my thesis. And